Hello and welcome everybody to this next edition of Laboratory Software. You already know who this is, your boy Laz, and today we're going to be taking a look at specific gravity of soils. Um, I'm going to talk a little bit about that when we get logged in and settled in and whatnot. I wouldn't doubt that this is going to be a fast one because there isn't a lot that comes with a specific gravity of soils, but I do want to explain the whole concept of it. Well, you know, to an extent, obviously. I'm always at this. No script. Okay. So, oop. All right. I guess that's just gonna do whatever it feels like doing. All right. So I'm going to open up this table here, and I'm going to kind of talk a little bit about specific gravity of soils. Oh, as soon as AVG needs to load up and tell me that, everything's on fire, because the world's always on fire, right? Anywho, so specific gravity in general, because you could do specific gravities on almost virtually anything. So the idea of specific gravity is determining what the density of that material, or what you're determining of the material, where if it's a liquid or a solid, what is its absolute, I don't want to say absolute, but it's almost what is its absolute density of that material type in general. And granted, since we're focusing on soils, these are the general types of soils that most are faced with typically around the world. So now, for specific gravities in general, usually they use it, it's usually determining the value with water, which obviously that's what we do as well when it comes to soil material. The only technical thing that we have to do on our end when it comes to soils is that it has to be deionized or distilled water. So, water that has no possible minerals or particulates in it that could affect the density of the soil, because obviously those minerals and particulates will add density to the water itself. Typically, the density of water is 1, and it also depends on what your temperature gradient is. So if it's, I know here for Fahrenheit, if it's 77 degrees Fahrenheit, your specific gravity of water is typically 1. So in most cases, so people don't have to worry about correction factors and whatnot, they'll usually typically try to keep their water temperature at 77 degrees Fahrenheit. And I can't remember how much that is in Celsius, because obviously I don't work with Celsius that often when it comes to the specific gravities and whatnot. So as I bounce around here, the whole idea of specific gravity, like I said, is determining density of whatever that you're determining, where if it's a different type of liquid or soils or metals or anything like that. And usually they check it with water. I mean, obviously you can use any other kind of substance. The only difference is if you use any other different kind of substance, let's say an oil base, well, the specific gravity of oil is different than what it is for water. So you would have to know what that is to dial it in, so you're not getting a false reading or anything. But typically everybody uses it with water and whatnot. So these values here, you can pretty much think of them as a factor. So typically for water itself, if it's at the exact temperature, like I said, 77 degrees Fahrenheit, your value is 1.00. 0.000, however many zeros. So that's when it's at 1. Granted, as the temperature gets higher, your specific gravity is going to lower because your water is slowly becoming into a gas because your water is becoming hotter. So, that's the thing to think about. I feel like this is something I've already covered already in one of the other things that I covered for lab, for any part of the lab software here. So, if your water is cooler, then that means your density is going to be higher because it's turning into ice. Ice is more denser than water, right? So, with that in mind, when it comes to soils, these are the typical values that you would get, as well as the range that you would get it in, typically depending on the soil type. So for sands, and if you remember all the way back when I talked about classifications and whatnot, so sands are materials that have a fines content that is pretty much less than 12% to 15%. Passing your number 200 sieve is what's generally considered a sand, at least for this here, typically. What thing? Okay, you're just gonna flash orange is going on, but then nothing's going on. So at least for this is what that is. Even though we know classification-wise, obviously you can have a sand with silt once when it passes 5%. But, when it comes to specific gravities, it's just determining what the general density is of the material, which I'm going to kind of cover into that a little bit more before we actually get into the meat and potatoes of the software itself. So you have silty sand, which that's anything that is above about 15%. Technically it could be like 15 to 50%. Passing your number 200 sieve, it's what is predominantly silts more than clays in itself, and usually you got a specific gravity value of 2.67 to 2.70. For inorganic clays, so that's just clay just as it is, no organics in it. As you can see, it's getting denser. So with sands, even though it's heavy and whatnot, this has a lower specific gravity than clays. And the idea is, well, I wouldn't say the idea. So the reason behind that is because, even though sands are dense, it's only the single grains and particulates that is in the sand itself. You have a lot of air voids that go through the sand. So this is why it's that low. When you look at inorganic clays, or just clays in general, you have 2.70 to 2.80. Because clay, there really isn't any air voids in clay, unless if it's naturally occurring in itself. But the clay itself, usually doesn't have air voids, so that's why the density is a lot higher than the sand. Okay, so we got soils with mica or iron. That's usually 2.75 to 3.00, which, obviously if you think about it, mica and or iron is, minerals. Minerals usually have a heavier density and whatnot. So you can almost think of this as if this is rocks or aggregate and whatnot. Typically have a range between here to here, which, granted, for the specific gravity of soils, this test method doesn't cover performing specific gravity on fine aggregates and coarse aggregate, or asphalt or anything like that. That's a whole nother different test method, and the procedures are done vastly different for that. And then, of course, you got organic soils, which is typically anything that's going to be less than 2.00. So if you think about it, when it comes to organic soils, when you have any kind of organic matter in general, I'm pretty sure you might have done this before in your life. And granted, this isn't what we typically deal with in the lab when we process soils and stuff. So Yes, there is grass and things like that that could be in the sample, but usually that kind of material is removed because we're trying to use it for construction purposes. So, but you still have roots and or the organics that have stained the sands that wrap itself around the sand that give it a an organic presence. So, if you ever just thrown grass in water, what does it typically do? It floats, right? So, this is the same idea here. Um, Granted, for the procedure, depending on what procedure, let me change that a little bit there. So, typically for organics, it has a lighter density than sands and clays and silts. So this is why typically when you do a specific gravity on soils, and if it's an organic soil like peat, which I've covered, in this series and whatnot, you can see specific gravities that are less than 2, which that's your dead giveaway right there. Where okay, we're definitely dealing with organic soils like peat. It doesn't mean that there may not be any sand in it. Obviously, if you want to know your sands to any kind of ratio like that, you do a sieve analysis. You do a sieve analysis, and then obviously your lab person would note if they want to know specifically if there's what they like to call fibrous material. And usually fibrous material is considered organic material. So like roots, twigs, wood chips, you know, any kind of wood fragments. That's typically what we see when it comes to organic soils. So yeah, so this is kind of the general um, table for what people deal with the most, and then approximately where your values should be. Granted, you can have a inorganic clay and it could be higher than 2.80, but if it is, then usually that means there could be something else in that clay that could be making it higher. These are just typical ranges for what you would see for these types of materials. And granted, this is just the most basic list that I can find online. That's a good enough reference to talk about what I'm going to be showing today, or what this program is going to be doing today. Because obviously I won't be showing nothing, for the test procedure or anything. That's already been done and whatnot. And we just want to see how the program works. That's the whole idea of this. But I thought it was very worthwhile to kind of cover just a little bit in detail on what we're going to be seeing and whatnot, because the process itself is going to be fast and how you're going to do it. So, let's get this program open and running. Oh, actually, you can just go to here, and then I should be able to go to, because obviously I haven't done this in a little while. So I think I just did it right here. Soil test. Hey, I think that's it. Ding, ding, ding. Alright, so specific gravity of soil solids. Perfect. Alright, so before we start filling all this fun stuff in and whatnot, so typically for this test method, obviously you have your AASHTO and your ASTM method. This typically follows ASTM D854 and or AASHTO's T100 test methods. They, at this current moment of me recording this, they are two drastically different test methods from one another. So obviously if you do an AASHTO T100 and if somebody wanted an ASTM D 854, you would probably have to redo the test again. The AASHTO T100 is very straightforward, very simple. There's really only one way on how you can do it. Unlike for the ASTM, you have a couple of different ways on how you could do this. And granted, it depends on the material itself, because if you're dealing with anything that is organic soils, as I indicated, you typically just want to process the material as is at natural moisture, so you get the most accurate specific gravity. I've done this before in the lab. I'm guilty of it, and because if you dry out your peat or your organic soils, it's pretty much going to become charcoal. And then when you try to do a test like this, most of your materials are just going to float, and the water absorption to get in there to find the specific gravity or the exact density of the material itself isn't really going to work, because when you get that moisture out, you can never get it back in again. So typically for that, you want to run that at natural moisture, and then you're going to do a hydroscopic moisture, which I've talked about before, like with hydrometers and stuff. And then from that, that's just going to give you a moisture correction, so when you get all your weights, you can correct them, and then you know exactly what the specific gravity is. Because I've had it happen before where I've kind of forgot, or I assumed that looking at the material, seeing that it was relatively sandy, but it was black and or dark gray, and at least with the color, which could indicate that it's organic. Or it may not have a presence of organic smell, where like it smells like rotting tree roots, or usually organics don't smell great. And obviously I'll dry it out and process it, and then get it in there, and then my specific gravity is like 0.96, and that means it's lighter than water, and that's not right. So. I'm guilty of it, so that's why, depending on the method, which granted for both of those test methods, it does indicate if you're dealing with peat-like material or organic soils, you want to probably try to do it that way instead of oven drying it in a 230 degree oven or 110 degrees Celsius oven, 230 degrees Fahrenheit. Sorry, didn't say what kind of increment that was. And then, obviously, we're only testing the material that's passing the number 10 sieve, and then we're going to use this fancy thing called a pycnometer, preferably a 250 milliliter pycnometer. Granted, for ASTM, you can use either a 250 or 500 milliliter pycnometer. Granted, if you go on with a bigger size and you want to use more material. Typically, your material size is about 25-ish grams. There's a plus or minus with that. And then for the accuracy of this test, since this is typically reported either... Personally, for me, I typically like to report out to the 10 thousandths place, but usually this goes out to the thousandths place of the decimal point. But yeah, other than that, for processing it, you got all kinds of different ways for how you can do it. For AASHTO, it says you're going to boil it for 10 minutes, but granted, that's after when you let it sit for 12 hours in the pycnometer with your deionized water covering the sample, but not filling up your pycnometer up to your calibration mark. And yeah, and that's probably a whole nother thing that I gotta say here, and that's you gotta make sure your pycnometers are calibrated. And calibration's simple. You're just filling up your pycnometer with your deionized water up to your mark that's going to indicate its maximum volume, or what its indicated volume, because technically its maximum volume is if you fill it all the way up to the top. So technically there's a scribe mark in the neck itself that it's up to the laboratory and or the technician that is calibrating your pycnometer to determine the meniscus line itself, because technically you can either calibrate it from the bottom of the meniscus or the top of the meniscus, which, remember, the meniscus is the curvature of water. That's what that word is. So obviously you would do that, and when you do that, you want to make sure you have it within a temperature gradient that your laboratory is typically kept at. So if your laboratory is kept anywhere between 20 degrees Celsius to 25 degrees Celsius, so that's 68 degrees Fahrenheit to like 78-ish degrees Fahrenheit, just going off the top of my head here, where your container and everything is going to be sitting out and it's going to stabilize before you're going to do your final weights and whatnot. You want to make sure that you check that water because, like I described earlier, your density of water changes depending on temperature. So obviously the hotter it is, the less dense it is. So knowing what the weight of your pycnometer with your water at that temperature is going to greatly help you get a more accurate specific gravity. As well as these specifications also cover a K factor, which a K factor is just a correction factor that you're going to apply, and that's mostly based on what the temperature of your water is at for that. So, which I hope everything's here, at least kind of taking a better glance at this. Hopefully this has everything that we need that should be able to calculate the specific gravity. And I see it does an average specific gravity. We're likely not going to get that because we're only doing one test, unless I repeat the same test over and over, but we're already going to know what the average is because it's going to be the same number all over again. So, yeah. So that's the overall test in itself. Technically, to process it overall, you're either going to boil it or you're going to apply a vacuum to it. I typically boil it with a hot plate, and and then depending on your test method, depends on how long you boil it for, as well as what is its stabilization methods and or period of time. Which, granted, the idea of your stabilization method is once when it gets back to that temperature gradient that you've determined for calibration. So obviously, if it's still too warm and if you have your temperature gradient between, like I said, the 20 to 25 degrees Celsius, and you're getting a temperature and it's currently at 27, well, you can't finish your test. You don't want to get away to that because you don't know what the pycnometer with the water, how much that weighs, because technically we're going to subtract that from the material of the soil that is inside the pycnometer with the water. That's why all that's very important. So, anyways, I think I've covered enough of the all the background technical jargon. Now we're just going to get down to the easy part, and let's see if this thing's actually going to do what it's going to do. Alright, so we got a description of our soil. Granted, I'm using a proficiency that I've done a couple of years ago and whatnot. So we're going to say orange filthy fine sand. Specimen number, it don't really matter. I'm just going to say 3. Okay, so volume of flask at 20 degrees Celsius in milliliters. That's very interesting, which I guess that would make sense. So this one doesn't even... Interesting. I technically don't have that information for that, but that's interesting. So you got volume of flask at 20 degrees Celsius, how many milliliters? So that's just what is volume of your flask. Never mind. I'm overthinking it. Never mind. This is for what I've used is a 250 milliliter. Yeah, never mind. I'm overthinking it. So technically, whenever you buy scientific glassware, if there's scribe marks, right? So if it's like a measuring cup, and it tells you however many milliliters or anything like that, usually they typically try to make those scribe marks at 20 degrees Celsius because the specific gravity of water is like, it's not exactly 1, but it's at a controllable enough range that either most labs are set to, at least when it comes to climate control, so the room temperature is somewhere near there, where if you pour in a liquid, Yeah, that's the thing too. This covers a variety of different liquids that you can pour into it as well, because specific gravity is 77 degrees Fahrenheit, so that's like 25. I think it's over 25 or something like that. I know I'm making myself seem stupid, but it's okay though. Um, I mean, you guys can Google this. Come on, there's conversions or whatever. I mean, I know I can do that, but I'm in the middle of my TED talk, trying to sound professional or something. As we're just demoing this software that I've never used before. So, anyways, a little bit of background here as I threw myself off for that one. That's very interesting that it asked for that. I wonder if it does something here to help with that. I think that's just extra information for the report in itself. I don't understand. So, anyways, with your variety of liquids that are typically in a laboratory, 20 degrees Celsius is typically the room temperature that most labs are set at for any kind of scientific glassware, where if you needed exactly 500 milliliters, as long as the liquid and your general environment is about 20 degrees Celsius and you pour it up to the 500 milliliter mark, that means you actually have 500 milliliters. Other than that, most people, at least in our industry, we usually don't bother with the scribe marks that are on graduated cylinders or just anything that has graduations. Typically, we just weigh it, because that's your most accurate thing. It's what it is at that time for the temperature and the density of your liquid that you're weighing or material. So, okay, so we got the temperature of the test in degrees Celsius, which that I have. So for this one, this was at 28 degrees Celsius at that time. Location, I don't really have one. Tested by yours truly. And the date, or we'll just use today's date. Alright, so here we got our volumetric flask number. Typically, that's whatever you write on the flask itself. You can identify it however in the world that you want. I don't know if this program's weird. Notice how I put specimen number 3. That's technically the flask number that we used. That's right. This ain't enter-friendly, right? 3. Yeah, no, this ain't enter-friendly. Okay, so now we have the mask of flask plus water filled to the mark, and the mark is exactly what I explained before. So the mark is what is scribed inside the glassware itself, and then it depends if you want to use the top of your meniscus or the bottom of your meniscus. But you just have to make sure whichever way, how you did it, when you calibrated it, is exactly how you need to do the test. Because obviously, if you're doing the top of your meniscus, then that means you don't want to do the bottom of your meniscus as you fill it up, because that means now you're adding more liquid than what it was calibrated to, and it's just going to throw off your whole specific gravity. So let's see, mass of flask plus water filled to the mark. So that would be as I look at my paperwork, 354.98. Alright, so, and now we have mask of flask plus soil plus water filled to the mark. So this is with us introducing our soil into the pycnometer. We added our deionized water, and then we've boiled it or conditioned it however that we had to. And the idea of boiling it or vacuuming it is we're just trying to remove all the air from the soil itself. Since the soil can have very small air voids, it's really mostly for clays, honestly, is where you have to worry about it. I mean, if it's sands, the air voids are going to get out a lot easier, even through just general agitation. But that's not part of this method. So usually it's with clays, because clays can have air voids, but remember, kind of like what I said, it's dense. So you have to force the air out, and that's why you can either boil it, because it'll force the air out, or you can vacuum it, which is your other method. So this, we have 370.60 grams of material. And notice for this test method here, at least when it comes to specific gravity of soils, you're going to the hundredths place. You want to make sure that you're very accurate about what you're getting, because we're reporting things to either the hundredths or not hundredths, thousands. No, hundredths. I'm an idiot. Yeah, hundredths. Yeah, because typically it's either reported to the hundredths or the thousands. I know I said 10 thousandths earlier, but I was thinking that wrong. It's three. It's three places out. Most people will do two, kind of like what we've seen in that. Usually, I try to report to three, and then obviously you can round it or just report it as is and whatnot. All right, and then after that, we got to determine the mass of dry soil. So this is the soil that got added to the pycnometer itself before we added the water and did all this stuff and whatnot. And this soil is typically dried in a 230 degree oven or 110 degree oven, Fahrenheit or Celsius. Fahrenheit being the 230 and Celsius being the 110. If you've been paying attention, I've already covered that around at the beginning. So yes, you have to know that. So obviously you're going to tear your scale before you put all that down, or for you to record this, because that's going to be part of it. So for this one, I had 25.34. All right, and then it calculates everything that we have. So I wouldn't doubt that it definitely needs this temperature, because with this temperature you get your K factor, and obviously we're not putting in a K factor here. So it's looking up a K factor on a table. Now let's see here. So it calculated a mass of equal volume of water as the solids, so which for that's your your W1 plus your WS. So your W1 is here plus your WS, which is your soil, which is pretty much the same as what this is, but then you're going to subtract it from W2, which here we got 9.7. And then here we got our specific gravity in itself for T1 for degrees Celsius. And that's just going to be your WS divided by your WW. So our so our WS is our mass of dried soil, and then our WW is oh yeah, our WW is here. That's right, that value. I was trying to see like where the hell is. Okay, yeah. So our WW is that, and then this is where we get. So we got 2.607, and then with this being at 20 degrees Celsius, which is our GS here. This is just saying times A, which our A factor. I'm not too sure about this, like where it's getting this from, unless this is actually applying the oh, here we are right here. So actually it does do a lookup. Okay, yeah, and the lookup is definitely a bit off, which makes sense, because technically on my form, or what I have for my final results, is technically 2.603. This is saying 2.602. But the difference here is, so this A is technically the K factor in itself, which I think it's taking from this here. So technically the K factor that I currently have is 0.99840, and this is saying this is 0.9982. So, For me, when I calculate, it's a 4, but it's very small. But even so, it's 2.60. So if we wanted to just double check real fast, I mean, you know, let's just check our table just to see what did we actually get. So we're in 2.60 right now. So technically, we're below our sand values, which at least for this range, that's fine. But it's still, classified. It's still within the sand range in itself. And it's like I said, for the table itself here, this is just general values of what you would see. Sands can be like 2.50 or 2.50 for a specific gravity. It all depends on what type of sand it is. Where did it come from? Is it silica sand? Is it a natural occurring sand? Is it a well-rounded sand? Whoa, can I move that? Whoa, it did not like me clicking out and coming back. It did not like that at all. Oh geez. So that's it. That's a specific gravity test right there. Whoops, not 3.70. Yeah, I'm just entering in the same thing again. See if what is going on. Oh, because I said 2334. It should be 25.34. Okay, yeah, there we go. Yeah, I mean, I'm not surprised. I don't think the print test thing is going to work because it's actually trying to look for a printer. And yeah, it seems that way. So I'm wondering if I change this to 25 degrees, what 9982. When we do 20 degrees. It doesn't seem to. I wonder if I got to put. Yeah, that's weird. I mean, so it is doing that, but when does this update? Because it's stuck. It's stuck like that now. So why is it doing that? I mean, granted, it's a however many year old program, and I'm going to scrutinize it. Aha, there we go. 1. Interesting. So it didn't change any of the other stuff, even though it's all the same values. I mean, it changed the last one, it kept that one, and it kept that one the same, which this makes sense for this here, for all that to be the same, because this is assuming that, hey, this is at 20 degrees Celsius is what this point is, and then this is your correction here, is doing that when you have your K factor and whatnot. It's kind of weird that it does this. I don't know if that's just a subjugated thing that people were curious about, or if this was something that was done in the past that was required for the specification, because usually it's just you go right straight to the K factor. I mean, you calibrated your pygnometers. Why would you want to know what it was at 20 degrees Celsius? That doesn't matter. It wasn't at 20 degrees Celsius. If the specification required for it to be at 20 degrees Celsius, then you would have to wait for it to get to that temperature or ensure that you have an environment that it can get to that temperature without it affecting the sample itself. So you probably don't want to put in a freezer or a refrigerator or anything like that. Yeah, there we go, man. But yeah, so this was specific gravity of soil solids. Told you this was going to be pretty straightforward and short. There's a lot of steps to the test method. A lot of people are afraid to do this thing, as well as not a lot of people do this anymore neither. It's a very important thing to know your specific gravity of soils, because when you know what your density is of your material, it helps classify it better for starters, because now is it a sand or is it organic. For proctors and stuff, it helps with determining your zero air void factor. In case you have a material that let's say you have a sand that's getting 110 pounds per cubic foot in the field, but your technician out in the field's testing the material and they're really only getting 107 pounds per cubic foot, and they really need to add, like, let's say 108, for it to pass density or something. If you do a specific gravity on that, you could determine, okay, well, if our specific gravity was 2.60, then you would, on the Proctor curve, it would actually have lines of what your zero air voids would be. And obviously, if your curve's touching or anywhere near your zero air voids, then that means in the laboratory, the material itself achieved zero air voids. It's quite possible, which makes it harder in the field because the field's an uncontrolled environment, unlike how the laboratory is. So I mean, specific gravity of soils is it's a very helpful tool, but for the time it takes to do it, and for, I don't want to say how insignificant it is, but at least for most engineers this day and age, they don't really care about that. They just like generally classifying material as such. Hey, it's a sand, and if they need a specific gravity for a formula or something, usually, kind of like what I showed you with that table, they'll usually have a table and they'll just say, okay, well, I think it's 2.65. And I mean, we do it often, even for the stuff that we do in the lab, because people don't really care about it being exact. And then, to pay for an extra test method for something to know the specific gravity of a soil, that's just, it's for in place or being built on isn't really useful as compared to if it was going to be utilized in actual construction materials. So like concrete or needed a specific density because it needs to shield like radiation or hold something or whatnot. That's usually when specific gravities are going to be important, because then there'll be a minimum or a maximum of what that soil needs to be within, or the type of soil that it needs to be and whatnot. But yeah, that kind of ends that there. So I highly doubt anybody has joined, as well as I just enabled direct messages and whatnot. So if people wanted to say anything or whatever, I do have that enabled. Yeah, I guess no questions. That's cool. No questions. There's no people to ask these questions. My favorite, a dead room. Like how I am on the inside. Very dead. Anyways, I hope you guys enjoyed this as much as I have. We're chipping away at this series. There's probably only 2 or 3 more videos left. Actually, I think there's only about 3 more videos left for this series and whatnot. So, we'll see however that goes. I know, next month we're going to start our server maintenance, and, we're still working out all the plans and whatnot. And I know as soon as we know what we're doing and if I'm still going to be doing any kind of content creation during the month of December, then, you'll see some more. But, there may not be nothing until January. Anyways, enough of me babbling and whatnot. I hope you guys enjoyed it. Definitely let me know what you think. I know, for everything that I do on the daily, for my day-to-day job, which is what I'm slightly sharing vicariously through these older reporting methods of yesteryear. They're long and they can be boring, and you could, obviously fall asleep or get confused about what I'm saying. So, obviously, you can engage. You can ask questions if you want and whatnot. I know I do these streams very randomly, which doesn't help people prepare. Give like an hour notice before I do it, an hour or less, at weird times, I mean, even right now, it's 2:55 in the morning of me doing this. So. But enough of me babbling, man. I hope you guys enjoyed this. I'll see you in the next one. Later.